This video is on the objective compute the value of the test statistic, which will be a z-value or a z-score for a hypothesis test for a proportion. Alright, so we're going to be doing a test about a population proportion instead of a population mean this time. And we're going to run across the standard normal distribution, right? The z distribution, and our test statistic will be a z-score. And that's what we're asked to compute the value of here. And it's just like t-score. It's just, how many standard deviations away from the middle are you? Away from the mean. So let's take a look at first problem here. So as usual, if you're unfamiliar with the objective or want to see more about it, click on More Instruction. Look at their videos, their notes, their examples, and hopefully those help. Alright, so here a hospital administrator claims that the proportion of knee surgeries that are successful is 87%. To test this claim, a random sample of 450 patients who underwent knee surgery is taken, and it is determined that 371 of these patients had a successful knee surgery operation. Now they go through the setup here for the hypotheses. Right, the claim is that the proportion of all knee surgeries that are successful is 87%. So if P is the proportion of knee surgeries that are successful in the entire population, the claim is that P equals 0.87, which is, you see, the null hypothesis. And then the alternative hypothesis, remember the null hypothesis and alternative hypothesis are opposing statements, would be that the proportion is not 87% or is different from 87%. And then this would be considered a two-tailed test. But we'll get in all those steps later. What we're asked to do is find the test statistic for this hypothesis test for a proportion and round. Alright, so in your calculations, it says round the value of the sample proportion to 3 decimal places, and then round your answer to 2 decimal places, your final answer. Alright, so again, I'm going to go to a piece of paper and write some of this information out. So again, P, our population proportion, sorry, let me grab a better marker, represents the proportion of the population, proportion of all knee surgeries that are considered successful. Right. And as I stated, there's as with any hypothesis test, you begin by identifying a claim to be tested or a belief to be tested. And the claim, again, was that the proportion of knee surgeries that's successful is equal to 87%, which I'll write as 0.87. And then once a claim is established, once a claim is identified, you determine your hypotheses. Right, null hypothesis, alternative hypothesis. The claim involved equality. So that's going to be represented by the null hypothesis. Right, so the claim is represented here by the null hypothesis, and remember, the null hypothesis, the equality, is what you're going to be assuming is true, and then deciding whether or not to reject that assumption later. So we're going to assume that the proportion of knee surgeries that are successful is 87%. And then these are opposing statements, right? So the alternative hypothesis would be that P is not equal to 0.87. Right. And then again, I said this earlier, from the way the alternative hypothesis looks, right, that tells you what kind of a test you're running, one-tailed or two-tailed, right-tailed, left-tailed, or two-tailed. When the parameter is not equal to some value, that is a two-tailed test. Alright, so I'm running a two-tailed test here. Then there's a significance level. Right, remember that alpha. Now this particular question isn't asking us to complete an entire hypothesis test. So we were not given a significance level. We were not given an alpha. But in the cases that you're not given an alpha, you can pretty well assume a value of alpha of 5%. That's a reasonable significance level for most tests. All right, and then a sample is taken. All right, a sample is taken. Now, this sample, they said that this person looked at a random sample of 450 patients who underwent surgery. So the size of the sample is 450. Now remember, when we're talking about proportions and successes, usually we let this lowercase x represent the number of successes. Hopefully this rings a bell. So in this particular sample, the number of successes here, they said of these 450 patients, 371 of those in the sample had a successful knee surgery operation. So x is 371, and then from this we get our sample proportion, right? Our p hat. And this was, or p prime. Remember, this was also denoted as p prime in some problems. But this was the sample proportion. What proportion of the sample was a success? And that's just x over n, the number of successes divided by the sample size. And they ask us in our calculation to round this to 3 decimal places, right? So what's 371 divided by 450, rounded to 3 decimal places. So let's do that here. I'll pull the calculator up. 371 divided by 450. Alright, to 3 decimal places, this is approximately 0.824. And I'll use this in my calculation of the test statistic later. Now, because this sample size is so large, and this percentage times 450 is definitely greater than or equal to 10, and the q hat 1 minus this would be 0.176 times this would be the other remaining people that are failures is definitely greater than or equal to 10. Remember, by the central limit theorem, if you remember the central limit theorem for proportions, the distribution of p hats, right? If I were to look at all samples of size 450 and look at all their sample proportions, the distribution of the p hats would be approximately normal. A normal distribution with a mean called, mu p hat and a standard deviation called sigma p hat, where mu p hat, the average value of all these sample proportions, was just the proportion of the population was equal to p. And this from our null hypothesis, we have assumed this value is 0.87. All right. And the standard deviation of the p-hats, right, of the sample proportions for samples of size 450, if you recall again, was the square root of p times 1 minus p divided by n. Right. So for this particular problem, this would be the square root of, now p, again, we are assuming from the null hypothesis that p is 0.87. So this is 0.87 times, 1 minus 0.87, be 0.13. Right. And then divided by the sample size. And this is all inside the square root. Okay. And I'll round this to 3 decimal places as well. I'm just going to re-enter this later too, but let's pull the calculator back on. The square root of 0.87 times 0.13 divided by 450, and again make sure all of this is underneath the square root. So the standard deviation of this normal distribution, these normally distributed p-hats, is approximately 0.016 if I'm rounding to 3 decimal places. All right. And I'll draw a little picture as well of this distribution of p-hats. So a number line here giving me different possible values of p-hat, for samples of size 450. We're saying, the distribution of these p-hats should be approximately normal. So another symmetrical bell-shaped curve. Underneath the peak is the mean value of these p-hats, which we're again assuming is 0.87. And then again the standard deviation is 0.016. Remember, for the normal distribution, underneath these inflection points, those values should be 1 standard deviation above and 1 standard deviation below. But we're trying to figure out, what's the z-score? How far away is our sample proportion? Our p-hat, for our sample was 0.824, which comes in over here, 0.824. So here's our, p-hat. And then the test statistic that they're asking us to find is the z-score of our p-hat. Right? So what we do is we're going to normalize, right? Change this distribution of p-hat, this normal distribution, into the standard normal, which is the z distribution. So I normalize, right? Change into z's. Right? So if I change everything into z-scores, right, now my horizontal axis represents z-scores. Still a normal distribution, but now, underneath the peak, what's the z-score of the middle? The z-score of the middle is, 0. And I want to know what's the z-score of our sample mean. So I'll call it z-test, right? This is the test statistic. All right, this is the test statistic. So it's z equals, now again, you're going to take your sample proportion, your p-hat or p prime, subtract the p, that's 0.87. This is from the null hypothesis, what you're assuming p is, and then dividing that by, the standard deviation of the distribution of p-hats, this square root of p times q, or 1 minus p, all over n. Right. So I'm going to punch this in the calculator and round to 2 decimal places they're asking us for. Okay, so I'm going to take in the numerator, parentheses, our sample proportion, 0.824, minus, and then the mean proportion, which we're assuming is 0.87. All right, so there's the numerator. Then how many standard deviations is this, right? I divide by, now you can retype this, but I'm just going to put in the previous answer. The previous answer on my calculator is that standard deviation. So it's negative 2 point, and they want to 2 decimal places, so 90. That is the test statistic. That's, that means that our sample proportion is, 2.9 standard deviations below the assumed mean, below 0.87. And that's pretty far away. Remember, usually if you're more than 2 standard deviations away from the mean, you're pretty far away. But then we determine critical values or p-value of this, and use those critical values or p-value to determine whether or not we're going to reject the null hypothesis and then form a conclusion afterwards. But all we're asked for right now is this, right? What was our test statistic? And I'll box this formula in too. Right, this is important. Okay. How you calculate the z-score for your sample proportion. Alright, going back to the website, to 2 decimal places, negative 2.90. And say, great, you nailed it, all that. And again, look at the calculation they went through, the exact same calculation I just showed you. Wonderful. And that's all you're asked to do for this objective, this kind of question. Hopefully watching me do this one and maybe looking at the more instruction stuff, that'll all help you out when you go about doing this on your own. And thanks for watching.